This episode marks the first part of our three-part machine intelligence series, where we talk about the future of computing and the future of how computers will grow and be beneficial to us. In this first part, we will talk about reinforcement learning and evolutionary algorithms. In the second part, we will talk about deep learning and the future of artificial intelligence. And in the third part, we will conclude with three concepts from three different areas of computing. One related to connectivity, another one related to hardware, and the third one related to software. Stay tuned for this. Now we have the first part of our machine intelligence series. Very excited.
Even though the human species has lived secluded from nature for quite a while, there is one feature that we not only share with everything that has ever lived, but this feature has allowed us to grow continuously and exponentially: evolution. But in recent years, we have been able to transfer this feature to one of our closest companions: computers.
The neuro machine learning disciplines of reinforcement learning and evolutionary algorithms use properties of biology and neuroscience to learn by trial and error and recombine the fittest algorithms to solve a problem. So instead of having to code every function by hand, this allows machines and algorithms to grow and learn by themselves over time. But what will the real-life impact of reinforcement learning and evolutionary algorithms be? Let's explore.
Welcome to the UTX podcast, where we present you a utopia created by technology, presented by your Techniax. I'm Ani.
And I'm Valentin. And today we're going to talk about two very important and exciting subtopics of machine learning: reinforcement learning and evolutionary algorithms. After introducing you to all the relevant concepts and terms, we will take a look at the industry today and its applications. After covering the challenges, we will conclude with our signature Utopian day in the life of a Techniac. Let's dive right into it.
So we have to start by understanding what machine learning is in the first place. And like the name suggests, machine learning is when a computer algorithm learns by itself. It improves over time by adjusting input weights and biases, and even the very mathematical functions that it runs on. This all to generate meaning from data, identify patterns, and make predictions about the future.
So the first ingredient for machine learning is math, and the second and probably most important one is lots of data. Lots of training data, which initially can be of any form. It can be text, pictures, or video. But it also has to eventually be normalized and transformed into vectors, matrices, and tensors of numeric values before being fed to any sort of algorithm. The algorithm, whichever it is, then applies mathematical functions to perform classification, regression, and clustering. So it classifies or clusters training data, or it predicts a numeric outcome. So machine learning actually has many overlaps with statistics, with the one big difference that approximation of input weights and functions is aided by new techniques and automatically performed by a computer, as well as then tested and optimized by further application of mathematical functions, the so-called loss, error, or cost functions, and approximations.
Now, traditionally, machine learning has had two major classes: supervised learning and unsupervised learning. In supervised learning, you have training data that is labeled. So the algorithm has already some existing inputs and outputs and knows the relation between these. One example is your spam filter on emails. To classify whether an incoming email should be classified as spam or not, you take a training algorithm and feed it previously classified emails. And these will already have been labeled as either spam or not spam. And you also give it some additional information, such as the time during which it was sent, the language, length of text, etc. The algorithm then gets trained to detect future incoming mails as either spam or not spam. On the other side, you have unsupervised learning. And this is a approach where you have training data that is not labeled. So basically, you're counting on the algorithm to not just find the hidden relations between input and output, but also determine what the result actually is. A very simple example are clustering algorithms. So let's say that you feed a bunch of data points as geographical coordinates to an algorithm with a clear task to cluster them into groups. Now, both the number of groups as well as which points belong to which groups, both of these will be determined by the machine learning algorithm, and this is what we call unsupervised learning.
So there is supervised and unsupervised learning, and the selection of the algorithm itself is one of the tasks that a machine learning engineer has to undertake. But however, most of his or her work is surrounded around everything that happens before the input data is finally fed into the algorithm. You could say 80% is related to this, where most of these 80% are data cleaning. However, the work that has to happen before something enters the algorithm also includes acquiring the data sometimes, loading it from a source, such as a database, into a development environment, performing cleaning tasks on it, as mentioned, and transforming it into machine-readable forms, which most of the cases is a vector, matrix, or tensor of numeric values.
Now that we know both the types of machine learning, there's a third approach that's very interesting in machine learning, and this is called reinforcement learning.
How does reinforcement learning actually work? Reinforcement learning is quite a new algorithm or a newer type of, not algorithm, but newer type of family of machine learning algorithms, or also a newer approach to machine learning. As opposed to extracting meaning from labeled or unlabeled data, reinforcement learning is about sending a computational agent to a simulated environment and having it figure out how to navigate that environment in an optimal way. So it's really modeling its decision-making process with the goal to achieve a maximized reward for that agent.
Speaking mathematically, this decision-making process is very important. And in mathematics, we call this a Markov decision process, or MDP. And the basic idea here is that you model the state of an environment over time. You have an environment that exists in an initial state, and you have the computational agent, which is the algorithm. And the agent makes an observation of that environment, which could be complete, but could also be incomplete information about the environment. The agent then takes an action. So in a 3D environment, for instance, like a game, it would be moving left or right, or maybe in a betting game, it would be adding numbers to their bets. And these actions by the agent then trigger the environment to change to a new state and release an immediate reward or punishment to the agent. And this process happens over and over. And the end goal of the agent is usually to maximize the reward that it receives over time.
Where all of this gets complex for our agent is because in order to have a good simulation, you need to model a lot of parameters. Not everything is clear and transparent from the beginning usually. So the observations that the agent makes are partial. He only partially observes, or it only partially observes the environment. Your observation of those is incomplete or partial. You do not have a full view on which actions you can take, as well as how these actions will impact your reward. You can choose from many different from many different actions from an action space, and you don't know how, not just how it impacts the reward, but also how it impacts the environment, in what state the environment will transition after the agent has undertaken the action.
This complexity is very important for the field of reinforcement learning, because it's important to know that reinforcement learning can't be applied to every problem. We can't just take reinforcement learning, apply it to every problem, and then expect it to be solved. For reinforcement learning to really be useful, the problem that you approach must be able to be mapped into a simulated environment where the solution is reached by a trial and error process, just as we mentioned before. Further, the problem should also have a sequential decision-making process. And this means that any rewards that are given for good behavior aren't all delivered at once, but are instead released after every iteration. And for multi-agent reinforcement learning with multiple agents, the problem should also incorporate the influences of the various agents on each other's decision-making. So for a single agent reinforcement learning, consider chess, where you have an agent using trial and error process by playing different games. Also, the benefit of each move is immediately given, and the environment adapts to each move in that the other side counters the agent's move with a move of their own.
So chess is also a good example of multi-agent reinforcement learning if you want to have two agents playing against each other and you want to model those two. But we're also going to go a bit deeper into multi-agent reinforcement learning later. Now, reinforcement learning has achieved the capabilities to simulate these optimization problems as games and thus model the decision-making process of agents inside that game to achieve what's called a policy, which is the optimal way that they choose actions in order to maximize the reward. But what if you now could also optimize the way these agents, or in fact any algorithm in any optimization problem, learns the best actions and policies, because that's what it's all about. What if you could apply the strongest force available to us to solve that problem? Well, let's enter the algorithmic power of nature.
And speaking of nature, we have this type of algorithms known as evolutionary algorithms. And these basically apply biological principles in the process of optimizing a problem. Now, evolutionary algorithms are meta-heuristic algorithms. And a meta-heuristic algorithm is an algorithm that doesn't solve the problem, but instead finds the best algorithm to solve a problem.
And in evolutionary algorithm solving, what we have is we have all those different algorithms that we can choose from as the population that we breed from. The principles of biological evolution apply. And these are breeding or reproduction, in this case between different algorithms, crossover and recombination of those algorithms, mutation, as well as, of course, related to it, natural selection based on the fitness. So at the end of the day, what you do is you initialize several algorithms as a population set of candidate solutions to solve that problem, but not to deliver the solution, not to be the solution, but to deliver the solution. And we also call this a chromosome. And what then happens is biology, essentially.
Exactly. So as you mentioned, natural selection or fitness is the next step. This so-called fitness function optimizes, or the fitness function is the function that these algorithms must optimize at which they must be best. And this function essentially determines the quality of each of the algorithm candidates, and it determines the probability with which algorithms are then selected as parents for the next generation. So think of it as kind of applying with your CV and cover letter.
And what the parents do, hopefully, is they breed. What is achieved in breeding, both in biology and also in evolutionary algorithms, is we do crossover and mutation between the remaining algorithms, between the remaining parents. This creates their offspring, which is a new set of algorithms containing elements from all parents. Crossover in this case means recombining algorithms with each other, and mutation means replacing some of the parameters of those individual algorithms to create new versions of those algorithms.
And finally, you take the bottom half or the least fit members, or in this case algorithms, of the population and then discard them. And you then restart this cycle where you replace these bad algorithms with newly bred members. And by repeating this process of fitness, breeding, then crossover, and then natural selection, you can finally get a very good algorithm. And this is ideally repeated until one member has achieved a certain level of fitness that you can predefine depending on your needs of the algorithm.
And interestingly, this member can be and probably is the result of reading, obviously, which is the result of several algorithms working together instead of just one. And you can do pretty interesting things with this, in fact, pretty neat things. And an example of this is the NEAT algorithm, which stands for Neuroevolution of Augmenting Topologies. So it changes the topology, so the structure of a neural network that it applies to solve a problem over time. If you think about it, our brain doesn't work that much differently. It also adapts its structure, which is neuroplasticity, during every encounter, every reference experience that we make with outside information to optimize ourselves or optimize itself in any direction.
Now that we have a good understanding of machine learning as well as reinforcement learning and evolutionary algorithms, let's take a look at the industry and who the big players are. And surprisingly, among the major players in this industry are the big tech companies. Google's AI research program, DeepMind, has created a lot of attention for reinforcement learning. For instance, they successfully beat the best human player of AlphaGo with this algorithm. There's even a documentary on YouTube that I highly recommend. So Google has been in the spotlight with DeepMind for a long time.
Big tech definitely has the most important resource that you need for this, which is a lot of consumer data. And in case of Facebook, Google is a little bit more secretive about how their search queries work, etc., how they are using their user data for good reasons. In the case of Facebook, at least we know quite likely for what they are using reinforcement learning, because they have also built an open source Horizon platform. And it allows anyone, in fact, also people outside of Facebook, to do reinforcement learning production and deployment of large-scale applications. It serves as the flagship for the firm's RL efforts. The company itself uses the platform in its own products to deliver more relevant notifications, to optimize video streaming, and to improve suggestions in their Messenger application.
And another big player from at least the big tech side is, once again, now the world's richest man, Elon Musk's non-profit AI, his research laboratory, OpenAI. And they are behind one of the most widely used reinforcement learning software development kits, which is known as the OpenAI Gym. It is an open source environment and interface that allows users to experiment with predefined reinforcement learning examples, but it also allows them to model their own agents using Python. And to talk about the industry, because this is a very new industry, or at least the technologies are still very young, it's really hard to find proper industry data. However, we have unsurprisingly found that this market will experience massive growth in the coming years. And we're talking really massive.
Exactly. We're talking about the machine learning market, and we're talking about massive, which is 40% CAGR per year. So you take something and you add 40% on top of it every single year. In 2016, the market size for machine learning was $1 billion. And it's expected to grow, or it has grown to a currently low two-digit billion-dollar market size. And if it continues to grow with this 40% CAGR, it will be $120 billion in 2027.
Wow.
We're pretty sure that the relative share of reinforcement learning and evolutionary algorithms of this cake will also increase massively with it. So it will experience even more growth than machine learning itself.
So moving on, now that we know how how they work, and who the players are, and how massively it's going to grow, let's take a look at why we're looking at 40% CAGR. Let's look at the applications of first reinforcement learning, and then we'll get to evolutionary algorithms. So reinforcement learning, one areas we did mention simulated environments. So obviously games are a great area of using reinforcement learning. Basically, anything that can be simulated in a game environment is suitable to be modeled in an MDP, Markov decision process, and thus is very suitable for application of reinforcement learning. We mentioned before Google's DeepMind that managed to beat the best human players in AlphaGo using reinforcement learning. And really, any problem that can be thought of as a game uh, can be used with machine learning. However, we find that the ability to model the environment and its states, as well as factor in the impact of the agent's decision on that environment, is a requirement to model the problem in an MDP, sorry. And this becomes a problem of itself. So just the very translation into a state of a simulated environment given MDP criteria. However, interestingly, there have been even useful examples in real life sports.
Yes, and the example that we have is again from Google, from their Google Research Football Department. It was a Kaggle competition that I personally participated in. Unfortunately, I didn't get the prize. And the competition was in cooperation with Manchester City. Manchester City reached out to Google for this competition, and they flown in the best participants on site to Manchester City to work together with them because they wanted to get fresh tactics and strategies for the football game. So what happened in that competition was that you would model reinforcement learning agents to play football against each other in a simulation, and you could actually watch those games. What this really shows is if a big football club like Manchester City reaches out to reinforcement learning for developing new game strategies and tactics, this really shows the potential of reinforcement learning to be applied to sports simulations and any kind of game, like Ani said.
And then we move on to robotics and industrial automation. This is another very obvious candidate. Back in 2016, researchers from the University of Berkeley in California trained a robot based on computer vision and reinforcement learning. And the robot's actions were influenced by raw video images, and it learned some optimal policies of adjusting its motor torques by making use of RL or reinforcement learning. And it actually managed to optimize for different complex mechanical tasks that are performed every day in households, like opening a bottle, removing a nail from an object, or hanging up a piece of textile with a hanger. So very interesting to see that maybe we could get robo butlers that will completely adapt to our needs within a matter of days.
Wow, sounds exciting. In fact, so reinforcement learning you can also apply to time series data, and more specifically to trading and finance, where you obviously have time series data. IBM has done so, and they've built and tested a trading system whose return was measured against reference market indices, against simple buy and hold strategies, and against other time series models. The model of the reinforcement learning model achieved to capture well-known trading patterns like the head and shoulders reversal pattern, which is not that easy to spot for an algorithm. An example for reinforcement learning based trading is the high hedge solution, that's how it's called, by the Taiwanese startup Kuchi. I hope it's Kuchi and not something else. And high hedge uses deep reinforcement learning to recognize tradable patterns from vast amounts of data, including trading data from exchanges, news about companies and about stocks, as well as macroeconomic and financial data.
We can also see reinforcement learning, or specifically deep reinforcement learning, and a short notice that if you want to learn more about deep learning, we will be releasing a video next week on deep learning, so stay tuned for that. But coming back to deep reinforcement learning, Even autonomous vehicles and actually, in fact, any autonomous mobility device can benefit from deep reinforcement learning, as has been proposed in various notable papers. It can be applied to the development of scenario-based driving policies for complex navigation tasks, dynamic path planning, motion planning, as well as the prediction of traffic actors such as other vehicles, cyclists, pedestrians, children, animals, etc. So first testings have already been or are being undertaken by AWS as well as Wave AI.
We have found a research paper where researchers from Microsoft Asia have shown that reinforcement learning can work well on news recommendations. What they did is they modeled the reaction of users to the news recommendations they were shown. Their reactions were the rewards that the agent that was showing the recommendations would get. Now, why is this an interesting example is the algorithm did not just model the next click, the next reaction of the users, but it took into consideration the sum, the approximation of the sum of all the reactions as cumulative rewards over time. And this is really something that distinguishes reinforcement learning, that the way that rewards are measured as cumulative rewards over time really speaks for a sequential learning process, and it speaks for the algorithm being considerate of not just one action, but the whole thing, the whole simulation of what's going to happen. So it can really optimize for the whole game. Another thing is that the reinforcement learning can balance between exploring and exploiting. So once the algorithm has built out its policy, which is its best set of actions in order to maximize its rewards, it can choose to, or in the process of doing so, in the process of building the policy, it needs to both explore and exploit, because without exploiting, it doesn't know if actually that's a policy, if actually it works well. And that's something also that is unique to reinforcement learning algorithms, that as a hyperparameter, as something that you put inside the system from the outside, that you decide how much it should explore and how much it should exploit. And thus it really performs well in showing different news content to the users, and also taking into account which news content they previously consumed.
Yeah, this is very interesting also because the next example that we found is very similar to this sort of recommender systems, but this was actually used by the Alibaba group. So they created a virtual Taobao. I hope I'm pronouncing that correctly. And it is essentially a simulated copy of e-commerce transaction data from the actual Taobao platform. And it's based on hundreds of millions of customer records. And they simulated showing result pages to a buyer requesting a certain, or they simulated showing result pages to a buyer who was requesting a certain product. And they successfully introduced reinforcement learning to learn and optimize the process of showing those items to buyers. And this allowed the platform to maximize their revenues. So a very useful application of reinforcement learning, not just for the platform by maximizing revenues, but also for everyday users like us, because we don't have to scroll through endless pages of products that we're not going to buy, but just by showing what we are most likely going to buy, also saving us time. So it's really a win-win situation.
The remaining 3 examples that we have for you from reinforcement learning, they are somewhat mind-blowing, but also we show them because they really show the variety of things that you can apply RL to. And in this example, Microsoft has used it to manage resources in computer clusters. The state space of that environment was given as the current resource allocation and the resource profile of different jobs that you would apply the computing resources to, that you need to distribute it on. And Microsoft has used deep reinforcement learning. So reinforcement learning where at some point you have a neural network with several hidden layers applied, probably to calculate the action space, for instance. And it did optimize the resource allocation of that computer clusters to those waiting jobs with the objective to minimize the average job slowdown. So that being the reward, the lower the job slowdown is, the lower the better the reward is for the agent.
And this next idea, I really hope that we can turn this up to 100 very soon, is traffic management. So in a multi-agent setup, reinforcement learning was actually used to optimize traffic congestions by modeling the RL agents as traffic participants, all kinds, across multiple street blocks, with one agent taking the role of the central traffic light controller. And the system was optimized for the delay for the traffic participants caused by them just waiting at traffic lights. And while the results aren't confirmed in real life, uh, they've only been tested in a simulation. It would be really interesting to see how a real life simulation would look like, even maybe considering that the algorithm actively uses cameras or other means of detecting real life traffic situations, creating an algorithm, instantly training it with the data as it constantly feeds, and then providing optimal traffic solutions to minimize traffic congestions. This is like something from science fiction.
And remember that we talked about multi-agent reinforcement learning. So several agents that optimize an environment together or that play against each other in an environment, which would be chess. In this case, we talk about an economic problem, and I haven't seen that before, but 2 years ago, I've myself written a research paper on how you could use several agents to optimize for climate change. And in this game that they would play, you would look at how they deplete the Earth's capacity to take up greenhouse gases. You do this based on game theory, where you say this is a so-called tragedy of the commons problem, which means that everyone is depleting this particular resource, so the Earth's capacity to absorb greenhouse gases, and no one's really looking at what would be beneficial to all of them accumulatively, but everyone is just maximizing their own benefit, not seeing that by doing so, they are actually doing the opposite. So you could really use reinforcement learning for political and economic decision makers and mapping those decision processes in simulated environments, which I also find particularly exciting. Obviously, otherwise I wouldn't have written the research paper on it. So that's really also something that could happen in the future when we think about applying AI to really important decision-making processes, talking about intelligence in our society, that we can model decision makers in multi-agent reinforcement learning.
Yeah, I think we really have the potential to bypass all sorts of collective action problems with reinforcement learning. So this is really interesting. Um, we'll link the paper in the description, so it's easy for you to find. And now we'll move on to the applications of evolutionary algorithms. So we just talked about reinforcement learning. Now we're going to talk about genetic or evolutionary algorithms. And even here, there are many interesting startup examples, one of them being Reverie Labs. I hope it's pronounced like that, Reverie Labs. They are based in the US, and they use computational tools to advance drug therapies, drug discoveries for cancer therapies. So they use these algorithms to compose new optimized molecules, which are not just stable, but also easy to synthesize. And this enables them to accelerate preclinical drug development, which is a very big deal because for most medical conditions, the name of the game is finding a treatment as soon as possible.
Most of these examples in evolutionary algorithms that we look at use the subset of genetic algorithms. Those are the most promising ones. And another example using a genetic algorithm is the startup called Dynamic AI 56. a startup from the US that uses artificial intelligence to automate business communication, okay? More specifically for customer care, internal support, and HR management. They deploy a patented genetic algorithm solution that continuously learns from human conversations on social media, voice, and email channels, and it finds the best candidate sets of algorithms in computational linguistics and machine learning to optimize this communication. It has proceeded to automate up to 80% of those business processes in real time. So think about all those annoying emails and customer support requests that you and actually no one has to work with anymore, but it's just getting automated. That's Dynamic AI 56.
And the next startup that we're looking at takes another big leap, this time to agriculture. So the startup is called Carbon B. They're based in France, and they apply AI and specifically deep learning and genetic algorithms to precision agriculture. And this means that they can analyze aerial scans to suggest precise interventions, such as applying pesticides, weedicides, or herbicides to automatically detect weeds and remove them. So these are just a few examples, but the very wide variety is mind-blowing.
Absolutely. Next one is also completely unrelated to the previous one. It's VeriKai from the US. It brings the genetic algorithms to the insurance industry by using it for a predictive risk tool. What it does, it does a personalized risk assessment and calculates the premiums for insurance clients by providing and analyzing personal data on dependents using genetic algorithms.
So as you see, this is I mean, let's put it this way: 40% CAGR is more than justified. I mean, the use cases are endless, and we're going to cover this next topic anyway. But I think it's pretty clear why reinforcement learning and evolutionary algorithms are so exciting. Especially, we've seen it in a few examples now. If you combine reinforcement learning with deep learning, you can enhance algorithms in classic AI areas of natural language processing and computer vision. And these are areas these are fields of AI where you can benefit a lot of people in widespread applications for day-to-day use.
We're focusing on reinforcement learning here, but these combinations that we're about to show you, a lot of it also applies to evolutionary algorithms. And when we marry, so to speak, deep learning with reinforcement learning, what we have is, as we've seen in the examples before as well, we have the capacity of reinforcement learning to model the decision-making process of an agent in an environment or in a simulated environment, married with the ability to perform with high-dimensional unstructured data to learn sub-policies, to learn, for instance, the action space, or to learn the state transition process of the environment by using deep learning. And deep learning does really well in general when you have high-dimensional data, so a lot of features, and it's unstructured. Then it does perform much better than the classical machine learning algorithms. That especially applies in computer vision and in natural language processing. Just to remind us that the deep part of reinforcement learning, it refers to utilizing deep learning, so essentially a neural network configuration with several hidden layers, which, by the way, as Anya already mentioned in our next episode, we will talk about that in much more detail, talk about all the different or the most important deep learning algorithms that exist. So reinforcement learning really uses those deep learning algorithms to estimate the optimal action policies, to estimate the different action the different actions that it can choose from, to estimate how the state of the environment will transition based on the actions taken. All of these things can be modeled in complex functions in high-dimensional state spaces. So this really helps to model those problems and those complex decision-making processes, and enhances the capabilities of RL to be applied to much more much more difficult, much more complex simulations.
Another reason, as we mentioned before with the examples of two algorithms playing chess against each other, traffic economics and game theory, is an MDP, Markov decision process, with several agents, which we call a multi-agent reinforcement learning algorithm. And with this, you really have the ability to map decision-making processes of several agents at once. And you can also look at how their decisions not only influence the environment, but also how their decisions influence each other, expectations, etc. So there's a lot of things that we can simulate in reinforcement learning, especially with multi-agent reinforcement learning.
Exactly, especially if we marry this with the language that we have to simulate diplomacy, or that we simulate those decision-making processes, which is game theory. If we apply game theory to multi-agent reinforcement learning, we can really go as far as to model, for instance, diplomatic processes like the one mentioned with the tragedy of the commons problem of trying to optimize for each individual's actor's behavior in terms of not depleting the Earth's capacity of greenhouse gases by not consuming as much CO2. Sorry, by not producing as much CO2.
Exactly. So from any collective action problem all the way to preventing wars. So we're talking not just on a software, me shopping on Amazon, but all the way to statecrafts and to the highest levels of organizations.
And note that obviously this is not the one size fits it all solution, especially because decision-making processes are not always taken fully rationally and based on full availability of data, but oftentimes a lot of other factors come into play. But at least there was the tool in order to show for what would be the optimal decision by modeling it correctly. But this remains a challenge, and we're also going to look at it in the challenges. You need to simulate an environment in a way that you actually have all those information, which is close to impossible, which is why reinforcement learning, in at least currently, has a long way to go still in order to solve all those problems. Spoiler, exactly. Now we've talked about how deep learning can help reinforcement learning, but reinforcement learning can also help deep learning, of course. And the classical deep learning applications that you need to look at, also in combination with reinforcement learning, is computer vision, where usually you apply convolutional neural networks, so neural networks that apply convolution and pooling in the process. And if this really sounds gibberish to you, then the next episode will help a lot with that. But time is a bit scarce to talk about all of this at once in this episode. And time series data. When we have time series data, recurrent neural networks that have some kind of memory, they are serving well for these problems. For instance, to optimize chemical reactions, which is also a process that happens over time, and where you can really apply reinforcement learning to it to optimize how the RNN, how the recurrent neural network does. Lastly, also you can even use it to generate art, or to generate anything, in fact, that is either similar or purposefully exactly like the thing that you fed the algorithm to, or that you fed into the algorithm, which is generative adversarial networks, where you have a generator which tries to copy what the input data that you get, but not actually copy the data, but copy the process of making that data. So it could be a set of videos or a set of art. And then you have an adversary that tries to find out whether this is fake or not. And what you do is you literally try to trick the adversary so that he can't find it out anymore. And also for this, to recreate variations of input data, recreate similarities of input data, to recreate the exact copy of that input data, but based on the process of creating it. This is also where reinforcement learning can come into play.
Exactly. We'll get more into these adversarial networks next week, but it reminds me of Turing tests where you just try to fool the other into tricking that it's an original. And also, speaking of generating art, a algorithm by Google actually recreated Van Gogh's Starry Night, and they look pretty trippy. you'll recognize the picture in an instant, but if you take a look closer, you'll notice that it's made up of entirely different elements. There are fish and other images in there made to look like the Starry Night. So it's very interesting to see how they perceive reality, or in how different ways they can perceive reality. There was even a recent article about how an AI was given the job to model a chair that looked like an avocado, and there were 20 or 30 different entries, and each of them looked very unique. That's a very interesting article you can find on the MIT Technology Review that I highly recommend. So now we come to the challenges. As usual, every technology does have its Achilles heels. We'll see that even reinforcement learning has its challenges. So one challenge is that reinforcement learning can only be applied to a very specific set of problems. We've already explored the criteria that a problem has to fulfill for reinforcement learning to even be an option. And beyond that, reinforcement learning also requires a lot of data to simulate such environments and train the agents. And today on Earth, very few entities have these large supermarkets and big corporations. And even though they have exabytes of data, it's impossible to recreate a perfect real life simulation. But in order for these RLs to be, or in order for reinforcement learning in general to be useful, these simulations need to reflect the real life circumstances so that they can also be applied in real life. So this would mean working with millions or even billions of records with thousands of state features and very high dimensional action spaces. So this is still a very large problem in fulfilling or achieving the full potential of reinforced learning as we saw it.
Especially when you try to model complex environments and not just something that is fully observable, like a simple game, but even something like Google DeepMind's AlphaGo was something that it was actually quite complex to accomplish, so that DeepMind was able to beat any human player in AlphaGo. With evolutionary algorithms, the challenges are also quite high. First of all, you randomly initialize them, so stochastically. You have trial and error algorithms with high computational complexity caused by having to evaluate the fitness for each candidate algorithm, because the fitness function determines who survives into the next generation and who doesn't. And it means designing efficient algorithms for them. Otherwise, they take a long time to converge. Sometimes the fitness function is approximated only in order to speed up the process. Also, the definition of a suitable fitness function itself, so defining what makes a set of candidates suitable in order to be an algorithm that solves the problem, is considered to be a major challenge in the field.
Exactly, but nonetheless, we think that we can hopefully overcome these challenges, maybe, and if not, at the very least, improve them and implement them to then live what we now call our favorite segment, the utopian day in the life. So it begins by waking up in the morning. So after I wake up, I talk and interact with my personal AI assistant, which not just supports me in everyday tasks, but also helps me to unload certain cognitive processes that are just mind-numbing and also more efficiently done on a computer. And of course, over time, this AI has learned my habits, reactions, and mood swings, and has optimized its actions accordingly using RL. And it also helps me schedule my day and optimize my schedule for managing my workload, achieving my goals, but still being able to be stress-free and enjoy my day.
So amazing, and I'm ready to go to work, and I take a robo-taxi. The robo-taxi learned how to drive almost fully based on simulations. It doesn't rely on driving millions of kilometers in real life, but the simulations that we've built in the meantime are so good that it can, based on reinforcement learning, fully converge into a safe and defensively driving autonomous vehicle by just by learning based on simulations. So I'm heading over to the strategy planning meeting of our company. Our business is going well as it relies on sophisticated strategy decision tools that simulate various market conditions in reinforcement learning scenarios. It converges to find the best set of actions that our company can take to remain successful. Genetics algorithms help us in modeling the correct assumptions, for instance, by learning the candidate set with the most accurate predictions against real life data.
And beyond that, whenever we launch a new product online, the RL automatically learns the very best channel strategy and targeting approach by using A/B testing, testing the different paths against a simulation of historical data that was provided to us by a social media company. So almost instantly, we are given the best channel strategy and approach to push our to improve our product launch.
I have some spare time during lunch and I watch the news hearing about the latest developments in regards to global climate change policy. Climate change, unfortunately, still is a problem. Nation states, however, now started to take coordinated action finally. Their decision-making process is aided by multi-agent reinforcement learning, as you can guess. And it automatically models and picks the best decision-making strategies for all of the nation states instead of individually for any of them. It optimizes the outcome for all actors under the ethical configuration chosen by the UN General Assembly, because you still need to determine what you mean by optimal, right? And so the UN General Assembly has decided that as well. We don't know if they also applied reinforcement learning to do that, but quite probable.
Yeah, and then it becomes late afternoon, and well, I thought it would be a good time to get informed about the latest trends in our industry. And my preferred way is to listen to it. And so a third-party provider uses genetic algorithms to extract and compile the best industry research and news from all different media and channels to a very short and succinct half an hour summary for me to listen to that I can just enjoy while taking a walk or on my way home in the car. And it's very convenient to be up to date on all the information that is relevant, not having to sift through mountains of newspapers and YouTube videos, but just getting to the stuff that matters. Very convenient.
Awesome. And I also could save a lot of time with it, which is now freed up to have some leisure activity in the evening. I grab some friends and head over to the stadium. There I watch a football match between two robo teams. Two local engineering teams that are playing against each other in the Robo League are battling each other. Their robots have learned the best action policies on the pitch by using genetic algorithms in a reinforcement learning simulation, and they made it to the final of the cup. What an exciting match to watch between these two champs of sporting intelligence.
It truly is a great day. And in the evening, I get a short summary of everything that was accomplished today, my outstanding tasks, of which there are very few left, and as well as a forecast for tomorrow's weather, what dress will be ideal to wear, not just to match the weather, but also to match my look because I have some meetings tomorrow based by also information on what the others are going to wear. I can go to sleep peacefully knowing that every decision taken today was some of the best, and that these decisions also helped make this algorithm that now helps me organize my life much better than it is already. So I go to bed very happy, looking forward to the next day, to the next utopian day in the life.
And you should be looking forward to the second part of our machine intelligence series. In the second part, we will talk about deep learning and the future of artificial intelligence. And in the third part, we will be looking at three more concepts, one related to connectivity, one related to hardware, and one related to software, which all of them will break computing and machine intelligence really to the next generation. Stay tuned for that.
And with that, we conclude this episode. We really hope you enjoyed it. If you did, please consider liking and subscribing. UTX has also started to create smaller clips for bite-sized information on the go so that you can get or extract your favorite bits of the UTX podcast on the go anytime. We upload these clips daily at 4 p.m. CET on YouTube. And we are also available on Spotify, Apple Podcasts. We even have a blog on Medium. And as always, stay utopian.
Your Techniax.